Okay, this is the lecture from September 13th, 2017, and we had a guest dog today. This is Maverick chewing on, oh, that's interesting. Yeah, anyway, he's chewing on a dog pizzle, or not a dog pizzle, sorry, bull pizzle. And then we used him to watch behavior, dog behavior, and then we also talked about his skull type. So I am doing, a voiceover of something here. So I'm going to start playing this and then talk. I had another technical difficulty today. I've got some kind of loose cable someplace. Anyway, so I showed him how to type in brachycephalic on the onelookdictionary.com, onelook.com. It's my favorite online dictionary. And so this is basically the name of the skull that the boxer has and other dogs that look like they ran into a brick wall, the shortened muzzle area. And then sometimes they breathe really, noisily, let's put it that way. Bulldog is another example of this skull type. So then Maverick was around and we were explaining the skull type, and now notice I'm doing a voiceover because of technical difficulties. And I know what I'm going to do now, what I'm thinking about it. I'm speeding up a little bit because I will not remember everything I said. And I think the student that brought Maverick was saying something about it. It's a white boxer. I cannot remember Maverick's age. But then we started getting into the lecture material, and I had trouble with the computer because some reason, Chrome isn't working when I log in, and I'm trying to work with the IT people about that. But we talked about, the previous lecture, we talked about LH, the gonadotropins, LH and FSH, and how if you had an animal without its gonads, its resting levels of the gonadotropins would be higher than an animal with its gonads. And so here I introduced the term overectomy. And I know I said you can do a unilateral overectomy in an animal, like maybe I use dog or cow as an example, or you could do a bilateral overectomy. And I remember I said it's different than a spay. When you have a female dog, for example, spayed, that's a little different than just a straight overectomy. So I'm typing in here LH surge because I want to find, I always say the Google image search is my textbook. And then I had trouble enlarging this in Internet Explorer, so I'm flubbing around here because my computer's not quite working right. And so I am going to point out the LH surge. I can point it out here. It's this dark purple, and this is actually in the human. The women still have the LH surge, but I think what I did is I tried to find an example from a cow, because a cow would be more straightforward and might show some more data as well. And so then I showed him this chart, and if I was using Chrome, I could enlarge that more. But I think I just said, let's use this here. And so the dark line, solid line, that is a peak there. You can see my mouse cursor there. That's LH. It ends up being, LH happens about the same time as the start of estrus. So they're coincident then. And I thought this was a cow. I think it's a horse, but this is going to work the same, except the length of estrus is a lot shorter in the cow, because I said the cow is in estrus about 18 hours. And when I was looking up at this thing on the screen, I said, oh, they either have a mistake or this is not a cow, because this OV here, I'm sure, is their depiction of ovulation. And ovulation in the cow happens after estrus is over. And anyway, estrus would not be this long. This is an animal that has like a 3-day 2.5, 3 days. So in class I said maybe it was a horse, but now that I think about it, it might be a sow. Anyway, I can't read the little print over there, but it doesn't really matter because the point is we were talking about the LH surge. And you have to have growing follicles on your ovaries to induce this LH surge. And I'm not sure if I said it in class, but only the female hypothalamic pituitary unit can send out a surge of LH. And this surge is different than the pulses that occur in a normal situation when there's not an LH surge. So we talked about how gonadotropins are released in a pulsatile fashion. That's not really shown here very well, but it does show the LH surge very well. And I pointed out on the y-axis the relative hormone concentration doesn't have, for example, nanograms per mil of serum, because we're talking about so many different hormones. Some of them would have different absolute units. Probably estrogen would be picograms per mil. Anyway, so that's why they're doing relative hormone concentration. You go up and that's higher, and then this is on the x-axis hours relative to estrus, and 0 would be the start of estrus. And then in this case, this animal has, 3 days would be 72 hours, so not quite 3 days, so that sounds like maybe a sow. And any animal that has like estrus that's 2, 3, 4 days or 5 days would tend to ovulate during estrus, but remember the cow would only have estrus to about this line. So then the cow would be in heat, out of heat, and then ovulation would occur sometime like that. And I tried to say that in a lot of cases ovulation, the period of time between the surge LH and ovulation is about 24 hours. And in this figure it looks like they've got it a little bit more. But I know in the cow it's pretty close to 24 hours. Okay, so then we're doing that, and it's not larger because my browser wasn't cooperating. I would have used Chrome, and then I know how to enlarge it in Chrome. So long story short, didn't get that enlarged as much as I would like to. Now I want to talk about the pig adrenal gland. And then some of these glands didn't really show what I wanted to, but this is a depiction, and again, too bad I can't enlarge it like I normally could. But it shows the adrenal gland sitting right on top of the kidney, on either kidney, okay? And so that's how it's always depicted in the human, but in like the pig, it would be up above here, cranial to the kidney, and it's kind of elongated. And so I was looking for a pig adrenal gland, but never found really a good one that I was happy with. But I did find a figure that introduced the concept of cortex medulla. And so if you talk about like the adrenal medulla, that's the center part, and it's neural, and the adrenal cortex is the outer layer, and that's pure basically endocrine tissue. So I'm pointing that out. I'm going to be skipping ahead. And then I found another nice figure. Again, too bad I couldn't enlarge it. But when you do a transverse section, you get this nice little demarcation between the medulla and the cortex. Cortex is also depicted over here, and there's 3 distinct layers of the cortex, but they all make a steroid hormones, different steroid hormones. And we talked about that. And so the adrenal medulla versus the adrenal cortex. The adrenal medulla releases the family of catecholamines. That's epinephrine and norepinephrine, or another way of saying that is adrenaline and noradrenaline. So hopefully people understand that epinephrine is adrenaline. So maybe more people use the term epinephrine. There goes my head because I did something with the camera. I have to reset a file size, but I did not realize it wasn't recording the sound. I might have a loose connection in a cable or a loose wire. Okay, so then after that I wanted to talk about an ELISA. and ELISA, you can see that here, hopefully. And I was trying to spell it out for people because it's really enzyme-linked immunosorbent assay. And we'll see, there it is. Enzyme-linked immunosorbent assay. So there it is right there, ELISA, sometimes called an EIA. And this is really enzyme immunoassay. So, but they're basically the same. And you take antibodies as part of the technique, and you have antibodies, in my example at least, attached to a plastic well in a microtiter plate. And of course, I don't know the audience if they know what a microtiter plate is, so I'm looking for some figures. And here, antibody, this bottom area is, think of it as the plastic wall. And antibodies can be attached on their stem region, and then the two antigen binding sites are out here, which can bind whatever they are made against. They can't bind anything, but whatever they're made against. In our example, I used progesterone. So here I found another diagram kind of depicting the microtiter well, plate well, and then here's the antibody, and then for this green portion here, I said that's progesterone. So if there was progesterone on the sample, it would attach there, one of the binding sites. And of course, there's thousands of these antibodies on the wall, not one, but when you're learning it from scratch, one is perfect. And then here's another antibody that's been added to the well, and it's got an enzyme attached in my case. And so this antibody wouldn't attach progesterone if there was no progesterone there. So like, if you put this molecule into this area, it would be washed out when you're decanting. Every time you do a step, you decant, wash the wells, and you keep going, going, going. Okay, so that's that. And I think what I did next is, if I found another one, or okay, I was showing people the microtiter plates. And these assays end up coming out with colorless substrate has been converted to a colored product, and you can kind of see how I'm pointing like these wells up here are basically clear, and then in my example we would say there'd be no progesterone in there. And then I introduced the idea of that you have a standard curve in an assay, and so that might be a duplicate there of standard curves. And then we always had like a high control and a low control. So like if we're doing progesterone, we would take some a large amount of blood from, let's say, a pregnant cow and aliquot it out to small samples, and then use it for a year or two. And always thaw one sample, put it in our assay, and it should be reading high. So pregnant cow, high progesterone. And then if we had some overectomized animals around, like a overectomized heifer or cow, then that would be low progesterone in most cases. But I did alert them to the fact that there are two other sites in the animal that can make progesterone, and so it's not pregnancy specific, which some people think it is, I guess, or use it that way, but you can get fooled because there's other reasons why progesterone's around, and it doesn't have to be in a pregnant animal. We're going to talk about reproduction later in the semester. So here I'm microtiter plates, kind of neat, 96 wells. So then I'm going to draw something, and the camera automatically focuses, and that's kind of neat that it did. Boom, yeah. So the autofocus is working. Chagrin to the sound. Anyway, I'm drawing one well of the 96 that are in a plate. And of course the walls would be even. I'm just, whatever. I'm making antibody attached to the wall that would come from like the company that makes these, let's say, kits. And I talked about how milk progesterone can be assayed this way, or you could do serum progesterone or plasma progesterone. So you have these Ys attached to the wall, and then the antigen binding sites there's two per antibody molecule. And what I'm in my black circle there, I'm going to say if we had a sample with a low sample with low amount of progesterone, maybe only one of the sites would be bound. to progesterone. And then I said if it's got a lot of progesterone, then all the binding sites would probably be taken up with progesterone, okay? So then you would let that reaction happen after you put your serum in, or milk. Then you decant it, taking everything that's excess away, everything that's not bound. If it's bound to the antibody, it's going to stay in the well. Then our next solution we would add is an antibody that's also against progesterone, but it has an enzyme attached to it, and that's what I'm going to be drawing here. So there's my Y with an E on there. That's my depiction of an antibody that's against progesterone, and it has an enzyme on it. So you would pipette that solution into all of your wells. Let's say you've got the 96 wells totally complete. And so I don't take time to do every site, but let's say there'd be enough antibody in there with the enzyme attached that it would attach to every progesterone molecule there. I just didn't draw it, all those connections. It would get messy. So then you let that reaction happen, and usually the assays kits say, do this for so long, and then you're going to decant it, because then you want to get rid of any excess antibody / enzyme molecule that's excess. And then you put a colorless substrate into each well, the same amount of colorless substrate, and these kits are all worked out well. And then if there's enzyme in the well, then it's going to change, in my example, to a yellow product. So enzymes are famous for taking a substrate and then converting it into a product, catalyzing it to a product. So then, in that case, in that example right there, if it's a high progesterone, then it would be high yellow. And I'm trying to refer back to the Microtiter plate that I was showing earlier. So in my case now, high progesterone would be high color. Low progesterone would be like clear. Zero progesterone would be clear. I also said there's probably 50 to 100 ways to do this. I didn't mention in class, but some of the assays, the more color means the less hormone that was there. So that's kind of funky. And I mentioned a kit that a company was selling years ago, and they were depicting it as milk progesterone, and if you took a sample at a certain time, you could say the cow was pregnant. And yes, maybe, if you take it 21 days or 23 days after you inseminate the cow and the milk progesterone is high, hopefully it was low at the time of breeding. If it's high, you might say the animal's pregnant, but there's a couple other reasons why it could be high. So it's not a definitive pregnancy test, and I think that's where sometimes people mess up, because they say progesterone means pregnant, and it's not. And I think class is over. See those people leaving, and again, I'm going to work on my sound thing. I got a loose cable someplace. I'm hoping this sound over works pretty good. I made this a little shorter than the actual class because maybe somebody had a question I can't remember.